Okay, thanks. And thank you for coming. And my name is Yongchang. I'm a first-year PhD supervised by Professor Lili Mo. And today I'm going to talk about our recent work named Low-rank adapters are secretly gradient compressors. And get my mouse here. What's that about? Okay, so you might have heard of a lot of large models like ChatGPT, like Stable Diffusion. And why do we have large models? That's because people find that by simply scaling up the parameters of neural networks, the empirical performance will be largely boosted. And this is an example from Google's text-to-image generation model. The task here is to generate a map of the United States made out of sushi. It is on the table next to a glass of red wine. So for a 350 million parameter model, here's the generation result. You can see that the model clearly does not generate a US map, and it does not generate sushi as well. But if we scale the model parameter to 750 million, then the sushi is roughly correct, but still the US map is lacking. And if we go further, you can see that, okay, now you have sushi, now you have a US map, but it does not understand a map made out of sushi. And if we go further and make it 20 billion, then this image is just what you asked for. So people find by simply scaling up model parameters, you can get better and better result for your task. So this is the model sizes by years. As you can see, the curve is roughly exponential by year. In 2017, the largest transformer model we had was 200 million parameters. But in 2020, we have GPT-3, which had 175 billion parameters, so roughly 1,000 times more. And last year, for GPT-4, it's rumored to have 1.8 trillion parameters. And it's hard to imagine, like in 2030, how large the model will be. But as the model grows larger, the hardware is not keeping the pace. This is a statistics of the maximum available GPU memory on data center. So from 2017, we had 16 gigabyte for Google GPU and 32 gigabyte for NVIDIA GPU. And until now, the maximum growth is only 1.5. So it's not a huge leap, unlike the model size growth. And for consumer level GPUs, it's even worse. So this is the statistics from a gaming platform, and only less than 5% of the users have a memory greater than 16 gigabyte. And 16 is not a great number. And know that this is a gaming platform, so people generally have higher end GPUs. So this means that with model growth larger, it's harder and harder for normal people to train their own model on their own device. And we probably cannot increase the memory of GPU because we cannot make GPU, but probably we can make some algorithms to reduce the memory requirement to train models. And to reduce the memory, we have to understand the memory usage of each part of model training. So here's a simple example of training GPT-2. And the largest GPT-2 has 1.5 billion parameters. And if you use half precision data type like float 16 or bfold 16, you will have a 3 GB storage to only store the model. And to execute autograd, you also need to save activations. So by activations, it simply means the input of each layer. And this part, if you use batch size equals 32 and sequence length equals roughly 1,000, then the activation may take up to 4 GB. And to train the model, you also have an optimizer. And Adam is the default choice, at least for GPT-2 and GPT-3. So for Adam, there are 2 statistics of gradient. One is the first moment estimate, MT, which is also called momentum. For this part, you can store it in half precision. And that will also cost 3 GB, exactly the same as a model size. And it also has another statistic called second moment estimate, which is VT here. And for this part, you cannot store it in half precision. You have to maintain full precision. And that will take 6 GB to store the optimizers. So this is a simplified example, but now you can actually see that more than 50% of the memory usage is by the Adam optimizers. So the question to reduce the memory usage of model training becomes, how can we reduce Adam optimizer while approximate the behavior of Adam? So in 2018, Shazier and Stern proposed adafactor. So what it does is that it factorizes the second moment estimate by 2 vectors. And ideally, we want this factorization to be linear. Like RNS, it should be linear in V. Why? Because if we want to update V, we cannot factorize this matrix every iteration. We want to update it fast. And they actually find something to obtain such a factorization. So they rely on the lemma, saying that if you want to measure, if your error of approximation is measured by the generalized KL divergence, I divergence, and your condition is, your factorization is non-negative, and also the regional matrix. Then the rank 1 factorization, so basically RNS are 2 vectors, will be this form here. So that means you can simply take R equals V projected by all 1 vector, and also S the same, but on the other side. And if you want to approximate V, you can apply this to get your approximation. So this is a closed form solution for this specific problem of non-negative matrix factorization. Okay. So how do they update the model, update the optimizer? As we see, Adam updates V in this form. And we now have R equals V projected by O1 vector, and S equals V also projected by an O1 vector. And by this form, we can apply the projection on both sides. Then we get a new update form, which only operate in vectors. And if we want to approximate the next V, you simply use RNS from the next iteration. So this is what they did. And what's the benefit of doing this? So for Adam, it has 2 states. One is the first moment, which is the momentum, and another is second moment. For adafactor, it relies on the non-negative matrix factorization to factorize one of them, the second moment, VT, from OMN to OM plus N. So basically, the memory for storing VT becomes sublinear. But one of the problems here is that it cannot factorize the first momentum, because there's no rule for like both positive and negative matrix factorization. In this case, if we want to obtain the real sublinear memory complexity, they have to turn the momentum off. And if you turn the momentum off, then the empirical performance might have some problem. For fine-tuning pre-trained models, it's completely fine. You can apply it to tune golfer models, can tune T5 models. But if you increase the model size, then you cannot pre-train the model anymore. So that's a cost of losing the momentum information in ADAM. And this figure is from a golfer paper. They tried training different sizes of model using ADA factor. And as you can see, the curve of ADAM is pretty stable, but the curve for ADA factor is fluctuating. So which part did ADA factor save? This is a recap of the memory usage of ADAM. And if we apply ADA factor without factorizing momentum, we will get a new memory size as large as 3 GB. That's obtained by not touching momentum at all, but factorize a second moment to very small vectors. And now, as you can see, it's only 30% of the memory during training is occupied by the optimizer. But still, we have something here, the 3 GB unreduced. So before talking about our method, I would like to introduce another way of saving memory. So if you have k parameters to optimize, then your optimizer will store 6k bytes of information in the optimizer state. And so one natural idea is that probably decreasing k is a good idea to reduce the memory usage. And how can we do that? In 2021, Hu et al. Found an efficient way, which is to apply a new low-rank adapter on the pre-trained model. So this blue matrix is a pre-trained weight with shape d by d or n by m. And what they did is they apply two additional matrix modification. One is A, you down project the input to a low rank space, and then you up project it to the original space and add them together. And for this practice, they only train these two layers, and they keep this frozen. In this way, they can reduce the parameters to be trained. And to make sure that these two matrices do not affect the original pre-trained model, they set B initialized as 0 so that you change the forward path at all. But to optimize, you cannot set both of them to 0 because in that case, you do not optimize at all. To solve that, they initialize A with a random initialization with Gaussian distribution. So this is a regional LoRA practice. Basically, there's an additional low-rank patch added to the regional full matrix. And according to their paper, such a practice is quite effective on fine-tuning models. But one caveat is that we only tune BNA in this W plus BNA, and BNA is constrained in the low rank space. So basically, you cannot represent any matrix W star that has this form. So if your rank of W star, the difference between W star and W has a rank larger than R, you cannot represent it anymore. And this includes very simple examples, like if W star is some scaling of W and W is full rank, then you cannot represent it. And also negation, the same thing. And even like random perturbation, you cannot represent it. You're unlikely to represent it with LoRA. So this means that although it saves memory, it suffers from the performance issue because the capacity of the model is restricted. So what we're thinking is if we can alleviate the low-rank constraint of LoRA, probably we can combine the best from both worlds. So the memory reduction of LoRA and the full capacity of a model combined together. Is that possible? And this is our intuition. So like with LoRA, what's the gradient of the regional matrix without LoRA? What's the gradient of the regional matrix? We just calculated with backpropagation or something. And it's represented in this form. And now with LoRA, what's the gradient for A and B? If you do some calculation, you can find that.
Sorry, what is L?
Oh, L is the loss function. And this is nabla, which represents the gradient. So you basically take the gradient of the loss function with regard to this W, your original matrix. And also for this one, it's for matrix A and B. Sorry, this should be B. So without LoRA, we have a gradient like this with shape n times m. And with LoRA, we have the gradient of A in this form by simple derivation. So if you look closely, it's basically the projection of the regional gradient by some matrix B. So for updating A, you project the gradient of B. For updating B, you project the gradient by A at that iteration. So this is by simple mass derivation. And our intuition here is that since B is initialized as 0, and if you calculate the change of A, you will find the whole thing becomes 0 if B is 0. And now let's look at the change of B. If A is initialized randomly, then the change of A will just be some random, change of B will just be some random projection of the original gradient. So this is the intuition. And in this paper, we formally show this with some theorem. And the theorem basically states that with some assumption that the model's trajectory is bounded in some space, then in this case, and your learning rate is small enough, in this case, the change of A is less than this thing. So there's a constant, a complicated constant. So we formally show that the change of A is less than this thing. And how do we use this theorem to show the intuition? We use it by inspecting the final update form of LoRA. So if you update A and B, you have a delta B for B, you have a delta A for A, and finally, you will get something like delta B A, delta B delta A, and also B A and delta B, B A and B delta A. But since B is initialized 0, so we just ignore the term. Now we only have 3 terms, W and delta B A and the delta B delta A. And now if you really look into this, you will find that for the second and the third term, this thing are the same. The only difference is that for delta B delta A, there's an additional term FAT. FAT basically represents the magnitude of how large A is changed. And in last theorem, we upper bounded the norm of this thing with some condition. And if we reuse a condition there, so the condition is basically the learning rate is small enough, then we can get this part, the norm of this part, times the learning rate much smaller than 1. So what does that mean? It means that if you plug this in to this equation, you'll find that the third term plays little importance in this form. Oh, so FA and FB is some form that we show the dynamics of B and A, BT and AT. And so basically it's a difference, but it takes A out, A0 out, and also the same for B. So it basically represents the difference of original A and B and the final A and B.
Why does the gradient of W appear in the updates for A and B?
Which one?
Right here, 5 and 6. Why does the gradient of W appear here?
Oh, so that's because of this equation. By a simple derivation. So if you calculate the gradient of A, then it will have this form. Because
W represents the whole parameter, not that pre-trained weight. Is W the pre-trained weight?
What is W?
W is a pre-trained weight.
Blue thing, right?
Yeah, yeah.
That blue thing doesn't affect orange.
Doesn't
There's no
affect.
arrow between blue and orange.
Oh, so the thing here is that if you calculate the gradient of W, then what's a gradient? If you calculate it, it's outer product of the input X and the gradient of the output H. So outer product of these two things. So it has nothing to do with the value of, it has something to do with the value, but if you have the gradient of H, then it has nothing to do with W. And this is the same for A and B. W does not affect the gradient of A and B if you have the gradient of H. Okay. Yeah, so by some basically rearrangement, you will get this equation that gradient of A will always be this, and gradient of B will always be that. And by applying this, we can get some dynamics like this. And by this dynamics, we form it in this way. And in this way, we show that the change of A is not that important if your learning rate is small. And so here's the intuition. If the change of A is not that important, why don't we just drop it? Okay, so why don't we just use change of B and the original A to represent the final fine-tuned LoRA module? Is that a viable path?
One more thing.
Oh, yeah.
What is the magnitude of FBT?
So FAT basically represent the difference between AT and A0, but scaled by this learning rate and also the random projection, because they use the same random projection. You always find the space of A0 there, right? And FAT is basically the thing that you want to represent. And so you can see if FAT, the norm of FAT is 0, then it means AT does not change from A0. And if it's small, then it means the magnitude of the changing is small. And if the magnitude of changing is small, you can see that the final effectiveness of this part is small in the trained LoRa module plus original pre-trained weight.
Norm of FBT is large.
Norm of FAT is B is large.
FBT.
That's that doesn't matter because for both terms you have FBT, and the only difference is FAT. If we can manage to get the upper bound of FAT, then we can get how large this term could potentially be. Yeah. So yeah, go ahead.
How do you ensure that the matrix AT can be represented this way?
AT can be represented this way.
And like the linear matrix product way. How do you ensure that? I mean, how do you ensure that FAT exists or something?
FAT exists. Oh, actually, we have a form of FAT. How FAT is represented by summing all of the matrices along the trajectory. So there's a form. There's a you can basically calculate what FAT and FBT is, and use that to get the norm.
As long as A0 has is invertible, then it exists.
Yeah, that's also correct. Yeah. Okay, any other question? Okay, so the intuition here is that the change of A, this part, is not important with this theorem. And so our idea is, if it's not important, why do we just make it frozen and only train B? So we call this method LoRa B, where we only train B in the LoRa module. And if you look closely to this, the change of B will be the random projection of the original gradient, nebula W of L. And if you replug this into the next W representation, you can basically see the difference of W is this thing. So that means it's equivalent to update W with the random projection matrix A. You down project it with this A0, and you up project it with A0 again. And you use this as the update direction of the original matrix W. Here, we use a frozen A. And another question is, can we resample this A0 to alleviate the low rank bottleneck? Because if you always apply the same A0, you can see that the whole thing will always be low rank, no matter how large, how far you go, how many steps you train, it will always be low rank. But what if we change this A0 at different steps? That may potentially alleviate the low rank constraint. Okay. So for now, we have several candidates in mind. We have LoRa, original, the conventional LoRa method, and we have LoRa B that we only train the B module, and we have RP, which is random projection, where we directly update B with the random projection of the gradient. And also we have RRP, which is resampled random projection. So the only change is that instead of using the fixed A0, we use different projections. And also the naive SGD as a baseline to see. Okay, with these candidates in mind, we conducted a preliminary experiment with a simple network on a simple data set, fashion MNIST. And as you can see, this blue curve is LoRa. So it's nothing too fancy, but it does not perform like very bad. And also this is pre-training, trained from initialization. So for LoRa, it's expected to not perform as well as SGD because of the low rank bottleneck. And for LoRa B, it's this orange curve. Probably it's hidden, but it's this orange curve here. It's a little bit above LoRa A. So that's our intuition too. It approximates LoRa, original LoRa, but it will not be the same because you will always have a fixed A0. But nevertheless, you can see that the performance is not much worse than original LoRa by simply training LoRa B. And we also see that this thing should be equivalent to random projection of the original gradient. And this curve is represented by the red diamond here. So you can see that the trajectory is exactly the same. They match each other. And what if we resample the random projection? Then you can see it drastically boosts the performance of random projection, down from the worst one to close to the best one, SGD. So that means by alleviating the low rank constraint of LoRa, by viewing it as a random projection, and by adding multiple random projection matrices, you can boost the performance of LoRa by alleviating the low rank constraint. Okay. So for now, we have verified 3 points. First one is the change of A is less important in LoRa. And if we just emit the change of A and make it frozen, then this turns LoRA into random projections. And we also show that by resampling the random matrix, then we can drastically boost the performance of LoRA, of the random projection, and even better than LoRA, by alleviating the low rank constraint. So here we have some simple ideas, but can we actually use this in the practice of deep learning? Before we go on, I would like to discuss how. So we view LoRA, or random projection, as two parts. The first part is compression of gradient. How did they do that? So if you look at the change of B, you will see that, okay, for every iteration, you calculate the gradient of W, and you project it, down projected from a higher dimension to a lower dimension with a random projection A0. And this practice is justified by JL lemma, or its variant. And here it's a random projection variant, and it basically says the norm of the down projected vector will be preserved in the lower dimensional space, the scaled norm. And if you want to see the update, then we show that it's equivalent to up projected again. If you up project it, the expectation will become this thing, a matrix like this. And in the paper, we also show that for this matrix, you will have a very high confidence that the difference, the element-wise difference of this matrix and the identity matrix, is smaller than an arrow. And as long as your dimension, the down projected dimension, is higher than C log 2m, and with some constant there. So it means that the down projected dimension only grows with log magnitude of m. M is a dimension of regional matrix.
In theorem 2.4, does R appear in your result?
Matrix sizes.
R, yeah. So R should be something larger than this constant. Than this
He's asking what
thing.
where does it appear in 18?
Sorry?
In 18, there's no R appearing, so.
Oh, 18. So the shape of A will be R times M.
So this is basically saying each row or column of A are perpendicular to each other?
Yeah, with high confidence, yeah. So in this way, we interpret LoRA into two phases. One is compression. You compress the gradient with some random projection. And for updating, you decompress it with this, as this matrix is close to the identity matrix with high confidence. That means it probably does not distort the original matrix too much. So to apply this in deep learning scenario, we found two ideal cases. One is a gradient accumulation, where for original gradient calculation, you probably have a batch of facts in forward pass, but that will take a lot of memory to store the activation. If you want to reduce that, you can use the gradient accumulation and take the average to approximate the gradient of that. But if you want to apply gradient accumulation, you have another gradient buffer to store the accumulated gradient, and that's the same size as the model. So we're thinking that probably we can compress this part, compress the accumulated part, to make it memory efficient. And also, another scenario is momentum in alpha factor that we just discussed. So how do we do that? Here's the algorithm for gradient accumulation in Flora. So basically, the general idea is that at each time step, at each accumulation step, we fix the seed, and we project the gradient down to the lower dimensional space. And we only accumulate the gradient in that space. And after accumulation is done, we up-project the gradient again to the original space. In this way, we saved the accumulation buffer of gradient. And this is a pseudocode for the algorithm. And how does this work? We had experiment across different model architectures on different data set, including summarization, the encoder-decoder architecture on summarization, and also the translation data set with a decoder-only transformer. And we also conduct experiments across different model sizes from 60 million T5 to 3 billion T5. And across all of the settings, you can see that our method, Flora, consistently outperforms LoRA, just like will be observed in the preliminary experiment. And when the rank is large enough, like when it reaches 1/4 of the dimension of the original full matrix fine-tuning, it will have the comparable performance in either root score or blue score, while having a lower memory usage. It saves around 30% of the original training setting.
So you know the time, does it save on time?
No, it does not save more time compared with, it saves more time compared with LoRA, because the thing is, we do not store the projection matrix, we store the seed. And the second is, we do not actually update A and B, and we do not merge. For LoRA, you have to calculate through two passes. For our case, it's still one matrix, and it has less flops than LoRA. But compared with the naive method, the original gradient, we only add the down projection and up projection steps. So it's not much longer, but yeah, it's slower than the original practice.
And you get similar results? Do you remember? How good are the results? Flora compared with Adam?
The final performance, yeah. So this is the root score. The root score basically measures the recall of summarization. And let's see, the largest model that we tried, the original performance of gradient accumulation achieves 44.4 on Roach 1. And ours, with rank equals 256, we have 44.3. So it's basically the same. And if you increase it even further, then you have a little better than that even. Although I would say they're quite similar. So with like sufficient R, you can replicate the result of the original naive gradient accumulation. And also the same for GPT models. And oh yeah, please go ahead. Saeed.
Can you hear me?
Yeah.
So about the experiments, I have a question. Are these like fine-tuning? And like how many data points have you used to fine-tune?
Oh yeah, so the question is whether the experiments are from fine-tuning. The answer is yes. This is fine-tuning T5 and GPT-2 on the different data sets. And the sizes of the data set is around 100K to 200K. But later we also have the training from scratch experiment on smaller scale model, because that will take a longer training time. Okay, so the second scenario is momentum estimation for add factor. In add factor, as we just introduced, we leave momentum unchanged or directly turn it off. So here with this random projection, we can probably compress the momentum as well by random projections, by different random projections. And the idea and the practice is quite similar to gradient accumulation, but one different thing is when switching the projection matrix A, we cannot do it directly, because if you just switch A without thinking, then you can imagine that for the next iteration, there's not much information can be decompressed with the new projection matrix A, because you use different, bases of the stored information and the decompressing information. So what we did is that we first decompress it with the old projection matrix and recompress it again. So in this way, we're trying to transfer the old momentum information into new one. Although this is still not very ideal, because as you can see, this A old and A new will probably have a very low magnitude too. But we argue that as long as this R is large enough, then the problem disappears. Because if R is large enough, you will always find something that is orthogonal in two matrices. Okay, so this is basically our algorithm for compressing the momentum state in adaptation. And what's the empirical result? We conducted an experiment with similar models on similar data set, but we did not conduct larger model variant because they're too time consuming. But we do have a smaller verification on 60 million model and 110 million GPT-2. And as you can see, so compare with no momentum at all, we are using more memory, of course, because we have to compress the momentum instead of dropping it directly. But we generally achieve higher performance of root score, even on small models. And also the same for this translation task. And compare with the naive momentum, which is used in adaptation, we also achieve the similar performance, but with less memory usage. So with our method, Flora, what's a memory usage of each part? We can see that for model, we did not change the model, so it stays the same for activation. But for optimizers, originally we have a 3 GB here. Now we only have 0.75 GB by setting R equals 1/4 of the data set of the matrix. And in this case, the total memory usage of the optimizer will only be 0.86 GB around. And in total, it only occupies around 11% of the training memory. So the optimizer part down from more than 50% to only 11% in training with Flora. And you may ask that whether this optimizer is general enough to not only text like a task, but also some other tasks. So recently we conducted experiments with VIT, Vision Transformer on CFAR 100 classification. For both VIT models, base and large, we achieve similar performance as Adam, while reducing the memory by 20 to 30% of the total memory usage. And also for training larger model, the largest model that we trained in the paper is 3B. So if we go even larger, how much it can save in that scenario? So compare with Adam, the regional Adam, this is the empirical result that we had on the 48 GB machine. For 3B, we have 11.25 GB, where Adam has more than 30. And for 7B model, we have 21, which is less than 24 GB, the largest available memory for a consumer level GPU. And while Adam had out of memory issue on even a 48 GB memory device. And we also predict for the 175 billion model, which is the largest variant of GPT-3, we would probably save 1.4 terabyte of the memory in that case. Although the performance of this needs to be verified, but we can see the memory reduction already on larger models. So can we further improve this Flora method? I believe so. So one of the possibility is that probably we can use better projection strategies. Now we're using Gaussian distribution to initialize the random projection. Probably we can use other distributions and even sparse distributions to accelerate training and reduce the storage. And this can be combined with previous work like very sparse random projection. And in the engineering wise, we can also combine it with quantization of optimizer's state. So we can represent the optimizer state with even lower precision to save even more memory of the optimizer. And probably we can integrate this with fused update optimizer, which means that you directly update the layer without storing the gradient at all. So all of these directions can be used to improve the existing massive Flora. And I would like to thank my collaborators, Yan Shuai, and my supervisor, Lili. The paper is now on arXiv. You can follow this link to see it if you're interested. And that will be all of my presentation. And feel free to ask me any questions.
So the reason why I can do this projection thing is because if like the first lemma ensure that, or the second theorem, the theorem ensure that you're able to sample a basis. If R is large enough, you're able to sample a basis. And with high probability, any vector can be projected this basis without too much loss of information.
Mm-hmm. Mm-hmm.
So
yeah.
Okay.
That's a correct understanding. So so actually there are two parts. The first part is the half part actually, the compression part. You have a projection matrix A to down project a vector from high dimensional space to low dimensional space. That is justified by JL lemma or its variant, where you can represent or approximately represent a higher magnitude, a higher dimension vector with some low dimensional vectors, right? You can approximately preserve information there. And the second part is decompression, where you want to reconstruct the thing with the compressed vector. And that part is justified by stating that compression and decompression, the matrix equals, or roughly equals to an identity matrix. Yep.
Do you remember those papers which talk about how the gradient lies in a low subspace? Do you have any comments on that? This looks like similar to that, right?
Yeah, I think in some theoretical papers, they claim that the gradient lies in a low rank space where you basically, it probably, you only update the model in the low rank space. However, empirically, this might not be very true. Like you can definitely get good performance with that, with the low rank gradient, but still, you do not, if you really make a low rank, then the performance, at least the empirical performance, is not very good, as shown in many examples, and also like our preliminary example, and also our real examples. And people use LoRA currently, which is bounded in low-rank spaces for fine-tuning only. You cannot actually pre-train models with the low-rank constraint of gradient. Thank you. Thank you for your comments.